In this video I will show how to model measurement results in Matlab as well as how to find the model with the best predictive ability. At first I will show how you can import the data of measurement file stored in Excel into Matlab. This Excel measurement table shows the results of the compressibility of certain powder formulation into a medical tablet. The compression pressure used in the tablet machine is stored in column A, and the strength of the compressed tablet is stored in column B. The numbers tell how many newtons of force the tablets must be compressed radially in order for them to break into two parts. In other words, it is the crushing strength of the tablets. The measurement data can be imported into Matlab by first pressing this Import Data button. After that, select the file from which you want to import the measurement data into Matlab. Select the numeric matrix option from the Output Type button and press the Import Selection button. Now the data from Excel file has been transferred to Matlab. The first column now has the compression pressure values and the second column the crushing strength values. Change the name of the variable to data with the rename command. By double-clicking, we can see the content of that variable, which is of course the same as the variable with the original name. And now a new program script is written. Where in the first row the numbers of the first column of the data matrix are read into the x variable. The content of the variable x is now the same as the first column of the data matrix. Then the second column of the data matrix, i.e. the crushing strength values, is read into the y variable. Then plot y values as a function of x values. We draw it with round black dots. Then we want also grid to the plot, and then we defined x and y labels and also the x and y limits of the axis. When you run this program, you will see a graph showing how the crushing strength increases as a function of compression pressure. Under Tools button in the graph, the function Basic Fitting is selected. Now the measurement results can be fitted using straight line or second, third or even higher order polynomials. Let's first try using a first order polynomial. We get the equation of the straight line and the coefficient of determination 0.9506. The model can be used to predict, for example, how strong a tablet would be if a compression pressure of 140 megapascal were used. The model predicts a crushing strength of 95.9 Newton. If you put 140 in the place of x in the equation and multiply it by 0.5 and add 25.07, the y will be 95.9. Then let's try quadratic model, because the response seems to be non-linear and it would seem that it fits better in this material. The coefficient of determination also increased clearly to the value of 0.9924. This model predicts crushing strength of 101 newtons at the pressure of 140 megapascal. In the same way as in the previous model, if we substitute x in equation with number 140, we get the value of y as 101. This model seems to be a better model than a first-order linear model. But does the model improve further if a third-order model is fitted to the data? This is a more complicated model and contains more terms. The coefficient of determination does not improve much. Let's try more complicated the fifth-order model, which should give an even higher value for the coefficient of determination. The coefficient of determination is now higher, 0.9976, and the model gives a prediction of the crushing strength of 105 newtons for the pressure of 140 megapascal. We can try a 9th degree polynomial, which is the highest possible for this material. Otherwise we run out of degrees of freedom. This equation still has one unique solution. The equation is already so complex that it is able to accurately pass through all measurement points, and the coefficient of determination is the highest possible one. But the prediction ability of this model is really bad. As a prediction at 140 megapascal compression pressure, it gives a negative value for the crushing strength of the tablet, which is of course impossible. That is, the R-square coefficient of determination is not a good measure of the model's predictive ability. It is better to use a Q-squared value like this, which better evaluates the model's performance. It uses cross-validation technology. Here you can see the calculation formula for Q-squared. There is no Q-square function in Matlab, but you can program it yourself. In the code I showed earlier, I have added the possibility to draw different order polynomials. In addition, the program also calculates the values for R-square and Q-square. You can see how these values change when we use different order models. Let's start from the equation of the first degree, which is the equation of straight line. R-square is now 0.95 and predicted ability 0.89. Let's try second order polynomial because the response is nonlinear. And it seems to fit much better to the measurement points, and the R-square increases to 0.99 and predictive ability also to 0.98. Let's try then third even higher order polynomial. The R-score is about the same, but the predictive ability drops a little bit to 0.96. Then we can try fourth order polynomial. Now the R-score increases still, but predictive ability drops quite much. If we now try the ninth order polynomial, which is highest possible, we get the R-score is 1, but the predictive ability is negative. So the best model is second order polynomial, which has highest predictive ability. Let's draw it. It's important to remember that R-score alone does not tell if the model is good, and if you make model more complicated, it doesn't guarantee always better model. In this picture, horizontal axis depict the complexity of the model, the amount of terms in the model. Vertical axis depict how big the value of R-score and Q-score are in this model. The more complicated model you use, the more near value 1 R-score approaches. When you get more complicated model, the Q2 value start to decrease in certain period. Then we start to overfit our data. The best model is achieved when the Q2 has its highest value. In this example, we have only one factor, but this same principle applies also with models with 2 or more factors. Also, in multilinear regression models, overfitting reduce predictive ability of model.